Hello. Okay, so I'm here to present some work on the emojinator system. It shouldn't be me standing here, it should be Marcia standing here, but she wasn't able to attend for reasons which I'll probably talk about in my second talk of the day. But for now, I'll be presenting this work, Emojinator, an emoji generation to represent emotions. Marcia makes an appearance halfway through. End of the talk. So introduce what we're doing and describe the problem a little bit more, just to round off some edges in the things that we're looking at. And then with Joao in the room, I don't feel like I have to really justify the importance of emoji generation, but I will anyway. And I'm going to look a little bit more about emotions. So emojis, emotions, right? And we forget that sometimes, and we're thinking of the little pictures that we're looking for. And then I'm going to hand over to Marcia, who will hopefully, technically, this will hopefully work, talk about the actual approach we took, the implementation work she did, and blending, and how we tested it with users. Then I will start to talk a little bit more again about the evaluation of it from a creativity perspective and wrap things up. Okay, so have a little Zoom thing that was hiding my words. So emojis means picture words in Japanese. I'm using these all the time. I don't think I write a text now without an emoji in there of some kind. I feel like it's sort of taken over my communications. So emojis have risen to prominence so quickly that it's been proposed as the fastest growing language in the UK. And so I with no justification world. And particularly the study by Dobler in 2015 found that a large proportion of 18 to 25-year-olds found it easier to express their feelings through emojis instead of through text. And so we are seeing a big boom in emoji-related tools, things like search by emoji, prediction for emojis in terms of what we're writing. Let's look at how we can tackle this from a computational creativity perspective. First of all, I don't know if you've had that experience where you want to put an emoji in that describes how you're feeling and you can't quite find the right one. There's ones that are almost there, not quite. We have, oops. And I do want to go on to this. So we have this problem where the emojis don't fully capture what we want to talk about when we're talking about our emotions. How do we get that into the computer? Well, that's a bit difficult because computers don't really understand emotion, maybe. So what emotion are we trying to express in the language that we're saying? And how do we depict those in an emoji? We're not tackling 100% both of those and focusing more on the emoji generation based on different emotional expressions in this. But our objectives for this project were to create the emojinator, the emoji generation system that can produce emotions to represent the wide array of emotions. We wanted to give the system some ability to make its own decisions. And we wanted to do this in a way which was creative, whatever that means. Okay. Why do we care about emojis, Joao? I feel a little bit uncomfortable talking about this work, given that Joao's primary research area is in this. So I hope I do okay. So our primary objective of emoticons is to take those emotions that we feel and put them in the little facial expressions. And this is important because it actually triggers off reactions in our brain, which are the same as well, close to the reactions that we receive when we see that expression in real life. So a study by Nusrat and Huang found that if you use emojis with messages in text therapy scenarios, it leads to the clients being more satisfied and ultimately willing to pay more and do recommendations, which makes money. Emojis make money. There's also the side of emojis that's more sociological. If you smile more frequently, you may be perceived as warmer, and that same effect has been found when emojis and emoticons are used. And linguistically, emojis aren't actually perceived as words, they are perceived as emotional information. And so when you're using emojis while you're communicating in text, that helps you to enhance the meaning of what you're communicating those emotions. I've convinced you that these emojis are really worth spending time on. So now let's look at emotions. There's lots of different ways that we can represent emotions. And I'm going to highlight some of the more significant ways of modeling emotions. Firstly, Ekman's model. So Ekman's model started with 5 and is now 6 basic emotions of, should I do the facial expressions? Sadness, surprise, fear. Out these emotions while I'm speaking up here. Happiness, disgust, which is probably in your faces right now at my acting, and anger. It's quite bad. But these 6 emotions have been found to cover a big space. Wang's hierarchical model of emotions classified emotions into pleasant and unpleasant. I don't find that quite so useful. It was wider in scope compared to Ekman because it wasn't just 6 emotions, but it was a little bit difficult to apply to this model because it didn't quite link up emotions and attitudes in the way that we wanted. And finally, Russell's circumplex model. It's a 2-dimensional model. The first dimension is valence, and so that is positive or negative, very similar to Wang there, but with slightly different interpretation. So delighted would be a very positive valence. Sad is a very negative valence. And the other dimension in this 2-dimensional model is arousal, and that's the intensity of motion. So calm is low arousal, and excited is high arousal, right? Too much acting, I know. So we used an update to the Russell's model for this work, Scherer's update. What Scherer did was to put a 2-dimensional structure onto Russell's model to actually put emotions in different places. Okay, it's far too small, but it will come up again, and I'll show it and it's in the paper as well. So you've got different emotions all over here. I'm going to zoom in on that a bit later. Right, hopefully.
Hi everyone, my name is Marzia and I will be taking you through the approach and implementation slides. So firstly, when it comes to the approach that we used, that was visual blending, and I'll be...
I can't get any higher on here. While I was getting this ready, it was really important to me that Marzia had some presence in this talk. So I asked her to record these slides.
Explaining this in the next, and I will be taking you through the approach and implementation slides. So firstly, when it comes to the approach that we used, that was visual blending, and I will be explaining this in the next slide. The computational tool that we used was processing, or specifically PY5, and for decision making, we ended up using fuzzy logic. So if I talk a bit more about visual blending is based on the theory of conceptual blending, and it involves basically blending or merging at least 2 images together to create a new image. And this was previously done in the system emogenating. We also see visual blending in emoticons. So for instance, I could change a sad face to a smiley face by just changing. Here is an example of an artwork of emojis generated using generative adversarial networks. The image on the left shows the one created from GANs, and the one on the right shows the normal emojis. And as you can see, GANs is slightly pixelated and not that good. And that was one of the reasons why we opted for visual blending. These are a few blends from the emogenating system. And as you can see, the first one is one for Peace Accord, Car Factory, etc. over here, we have some of the features that we used in our system. So what we essentially did was that we identified the different kinds of features that exist in an emoji, and these were then merged together. So if I see the first one, I have the different kinds of eyebrows, eyes, and all of these lead to an emoji at the end. When it comes to implementation and the features of an emoji, we identified the various features by mapping the existing emojis on the circumplex model and identifying the similarities that existed between different emojis. So this was a key diagram in our research because it helped us to understand the differences that exist between different emojis, as well as finding the similarities that exist between them as well. When it comes to decision making, we ended up using fuzzy logic. A key reason for this was that while crisp logic is very specific, fuzzy logic allows us to make room for imprecisions. So for instance, if I take an example of someone who's getting her dissertation grade, she would, if it was crisp, if I was using crisp logic, I would simply say that if she scores a mark above 70, she will be happy, otherwise she will be sad. However, with fuzzy logic, it would be something like if she scores a mark above 70, Sarah would be happy, but she would also be a little sad because she was expecting something above 90 perhaps. So that is where fuzzy logic comes in, because it's very similar to how our emotions are as well. And we ended up using trapezoidal membership functions. So we have a graph here as well for both balance and arousal. And the output values were depicted using the emotional state. And we had 5 membership functions. For rules and uniqueness, we basically implemented a particular set of rules. So fuzzy logic would allow us to determine an overall emotional value, and that value would make a decision about what kind of features an emoji should have. To ensure that every emoji was unique, we also added a weight parameter, which was determined by the arousal value, and that would impact the stroke thickness or the diameter of a particular feature to ensure uniqueness. So over here, we have an example of 2 emojis for embarrassed and felt guilt. Although they look very similar right now, but if you zoom in closely, there are slight differences. However, the close resemblance of the 2 emojis is one of the limitations of this research paper. When it comes to user testing and analysis of responses, we had 3 sections in our study. So the first section evaluated emojis based on how well they represented the stated emotion. We used the emotions are usually ordinal in nature. The second section compared emojis that were system generated with existing emojis, because existing emojis tend to be a benchmark. Participants, which emojis were system generated and which were the again ask them for their opinions while also allowing room for open-ended feedback. Our overall responses showed that 7 out of 12 emojis, at least 50% of the participants agreed that the emojis represented the stated emotion well. These were some of our top 10, like these were some of the emojis that we used in the first section. If I move to the comparison with existing emojis, we can see that the blue bars show us the results for the existing emojis, and the orange ones show us the results for the system generated emojis. And over here we can see that participants clearly preferred the ones generated, the existing ones. The only exception to this rule was the pensive emoji, which over here you can see that more people voted for the system generated or the emojinator one. Just to summarize the results again, I already mentioned that more than half of the participants agreed about the emojis. Participants also tended to like the emoji generated ones more once they were told that they were system generated. So that shows that there was possible bias on the part of the participants. Um, Participants were also perhaps used to emoji renderings on different operating systems. So for instance, Apple phones and Android phones may have different renderings of emojis. And one last thing is that a person's interpretation of their emojis is also affected by their age, where they live, and other social factors as well. Hi everyone, my name is
So just to finish off from me, so thank you, Martia. Yes, but how creative is our system? So we looked at this a couple of different ways. We looked at it, well, mainly we looked at it through the creative tripod. So is the system skillful? It's a bit limited. It's got some skill, but it's a bit limited. Is the system appreciative? Well, it knows it's got to generate the emoji based on what valence and arousal values it receives, but it can't estimate its own value. And is the system imaginative? It does generate unique emojis, but there's some similarity across the outputs. The fuzzy logic gives some autonomy, but again, by the human being. And in the user study result, give us a little bit of critical reflection on what we did. We compared 4 emojis with existing emojis, so emojis that exist in the real world already. We could have done that with more. It would have been better if we'd used a ranking approach to see what's the second best emoji, what's the third best emoji. So certainly there's limitations in the study, but we do feel that this work makes an unique contribution to existing research using the fuzzy logic. This is giving us the potential for how emojis can be used in computer-mediated communication with enhancement from AI. Get a bit more creative with our system, but it's a lovely step. And I think that when we're working in this area a little bit more in the future, taking into account relationships with emojis and social factors, sociocultural factors, is going to be super important. So thank you very much.
Thank you, Anna. We have time for a couple of questions. There we go. Oh, you get.
Scared. I want to say also, Zhao was really, really communicative with Marzio and I during the project. So thank you very much for that. I am.
So first I would like to say thank you for the lovely presentation and for the acting. I thought it was amazing. And bring emoji back to ICCC. I was done with it. I'm glad to see it coming back. It's a pity that Marcia is not here, so I'll have to direct the questions to you. I just have a small remark, which is, so based on the results, people would actually pick the existing ones, right? And from what I saw, there's a particular mark in the face that seemed to have a lot of importance, which is the eyebrow, right? So did you do this analysis of looking at the results and trying to figure out what is making this difference so big? Because, for example, in my work, so first, I'm not an expert in emoji, okay? I like emoji way too much, right? But I also got emoji into visualization. And it's related with one thing which is called the Chernoff faces. I don't know if anyone knows what that is, but it's a visualization technique that uses faces to represent multivariate data. And one thing that's interesting is that they pick on the idea that there is different salience in the parts of the face, right? So a smile has much more salience than, for example, a nose or a ear, right? So my question is, did you, after getting these results, did you actually look at the faces and try to identify why these results were like this?
Yeah, I didn't know about the, did you say the churn? I didn't, Chernoff. We'll have to have a look at that. Oh, I don't know if we can, this is where I try and bring up Marzio's slides here that she's presented. So we've noticed that because we only took a very essentially of the emotions, we took the eyebrows, the eyes, cheeks, and the mouth. There's a limit in the combinations we can get out of that. Again, essentially, it's a combinatorial problem, right? We have only a certain number of combinations available, and that led us to the similarity. One way we could have taken this further is to do what emoji designers have done and start to really explore things other than those basic bits. And we could have gone a lot more along the lines of, yes, but what makes that emoji so far away in valence from that emoji? And that could have related to which bit of the face we were looking at. That's probably something to persuade Marzio back for a PhD, but that is a good idea. Thank you. Or maybe for you.
Okay, I know there's some more questions, but I think in the interest of time, we have to move on. Sorry, everybody. Grab her in the coffee break and ask your questions. Okay. All right, everybody. Our next talk is by Waltiero Colombo. who's going to talk to us about exploring human models of innovation for generative AI.
Become admit, not admit.
Altiero.
Okay, so I'm Gualtiero Colombo. I'm from Cardiff University. This is like position work is more like concept. We are applying some method of cultural evolution to evolution of generation of images, and it's done with Professor Roger Whitaker and Dr. Hunter Liu, both from Cardiff University. A bit of background just to start. I'm pretty new to this field of real AI. I've been mostly working in agent-based modeling for the last 5-10 years, and always multidisciplinary work with psychologists, sociologists, anthropologists, and we were trying to build a computational model to model principle for mainly social psychology, like evolution of prejudice, evolution of bias, identity fusion. Some of these work they were quite successful with the prize. More recently, we got interested in cultural evolution as a mechanism for evolving innovation for existing cultural model. Basically, is about how culture change in terms of anything can be related with culture, so beliefs, knowledge, skills, customs, and so on. There are few, I would say, cultural evolution models towards like the more traditional evolutionary model. Some other they lead more to neuroscience. We refer to this cultural evolution model that comes from Boyd and Richardson, and then also Alex Mesudi for Exeter, which we put a proposal within recently. To identify two main mechanisms of evolution of culture. One is called cultural selection, is basically something really close to social learning. So imitating and copying existing cultural model. The other one is more related to bio. It's not very important what cultural model you try to imitate. You can imitate any, but then the cultural model is heavily transformed by your inner interested. We can talk about intrinsic motivation, bias, and things like that. So how to apply that to the evolution of images was the task. Of course, this slide just say that is cultural evolution is also evolution of innovation in culture is also related an evolution on creativity of generation of new idea. There was this seminal work with Boden, spelled badly, that was said that in computer, this is an old work from 2009. She was trying to classify how computer models and AI, the AI at that time can apply to creativity. And she classified into a field of an area that combinations on the combination of new ideas, association of ideas, exploration when is a step further. So you go back to some existing cultural model and try maybe to use it in a different context, in a different setting. And the real creativity would be like when cultural models are transformed. So new things are introduced, like new styles. And she was questioning if this would be ever be possible to be done by a machine. So that's what we're trying to explore, but we take a very simple setting of evolving images just to explore this. And the idea is let's try to generate images following this principle of how humans evolve and innovate. So we apply basically this simple model of cultural evolution, starting with some images. So the images that they produce are really basics. This is a computational pattern producing networks. There was some literature about 10 years ago also about that. And there was also an online experiment, which I'm going to talk in a minute. We start with only one hidden layer and four hidden neurons, and is able to produce abstract images like the one you see on the left. This neural network can be mutated, can be put in an evolutionary framework, like if it was a framework of normal agents. there is this field of neo-evolution that discuss explicitly how we can evolve neural networks, and applies to these neural network the genetic operators typical of evolutionary context, like a mutation and crossover. So with the mutation applied to a neural network like that, it will be maybe adding a node, removing a node, adding a connection, removing a connection. And crossover, you just try to mix, to merge different parts of two different CPPNs. There was this experiment, I think that was started again 2011 or something like that. And they had these images, but there was like a co-creative environment. It was a participatory experiment where agents, subject that participated in the experiment was selecting one of these images. They were maybe mutating it, crossover, exchange it with with another one. And then they produce a number of that, select the one that they most, move forward. So this experiment lasted for a few years. And the idea was that then a new subject comes, maybe picks an image that I have mutated, he mutated in another direction, and so on. And eventually led to, from the basic image that they started, led to some interesting images like the scalar that. There were a few attempts in the literature to reproduce that automatically, so in an automated way without involving humans. And they were really successful. So inspired by that, we do something similar, but we are not really interested in what we are producing. We are more interested in the methodology that can lead simple neural network and a simple CPPN to evolve in some direction. So these are some of the images that have been produced, and they can be plotted, they can be clustered using a similarity like embedding produced by the ResNet. And there are also existing framework that the one we're using, the knit Python, that is basically a framework, basic framework. On that, we added what there are actually two methods of cultural evolution, cultural selection, and bias transformation can evolve. First of all, we just showing this in this one how a random mutation of one images can lead. As you can see, after only few steps, the random mutation is not able to generate anything interesting, even if we start with images that can be of more interest. So this different approach is use what we call our adaptation of bias transformation. So basically, it's still starting for this simple random structure, but try to evolve it to a number of steps in which the image produced is driven. So it produces like a pool of images, and we select prior images that they are the ones that will guide the selection. So instead of the idea is instead of randomly transform the images, we guide the transformation with some given images like these prior images. And also we apply crossover within the structure of the simple random network and the structure of the prior images. It's important to say that all the images that I'm showing here are all generated from scratch, starting from some started images. As you can see, this is more shapes seems to emerge, and maybe more interesting figures seems to emerge. So this was like evolving a single question, a single images, but then we try to apply to a population of images. We start with 50 images where we can actually define better what are the methods, what can be the implementation of cultural selection and bias transformation. The principle of these two techniques is simple. In cultural selection, we try to select, so if I have a prior images, so an image that I was to guide the transformation to, so I want to transform the random image to something that is more or less similar to my input image. With cultural selection, I just select one of the images in the population that is the closest in similarity to my images, and then I mutate a random. Bias transformation does the opposite. It selects random from the population, but it heavily try to mutate and transform in the direction of the given image. So this sort of animation I explain clearly. So this is cultural selection. So at a population of random images, I got more than one prior images. In our results, it seems important to have more than one prior images. So because if we guide the selection just with only one reference image, that's instead of enhance creativity, can kill creativity. So because we are not after like copying the new images, but if you alternate the prior images with one other or more than once, This seems to stimulate more creativity, create a sort of tension, like we see in some plots later. They might generate more interesting images. So that's the simulation, what do you say, the first step of a cultural selection technique. So we start with an initial population of random images. I go for prior images. I select in this generation one of the prior images. I will select from the population the one that looks more similar. In this case, is this one. Then apply random mutation. So I mutate just a minimum. So you can see the shape is changing. So the figure is changing, but maybe not much. And then again, I do that a number of times. So I produce a poll, a collection of unique images, and some of them, they will replace the images then eventually in the population. And that was also the initial generation. You can imagine this process repeated a few times. So with bias transformation, as we say, is kind of the complementary one. So we start with still the initial population of images. This time we also select one out of the prior images that guide our transformation, our image generation. Here it doesn't matter which image I select. I select any of them. It doesn't necessarily be the most similar to the prior image. Actually, it's better if it is not. But then when it comes to the transformation, this transformation will be heavily influenced by the prior images. So we apply a crossover with that prior images. In the paper, there are actually 2 or 3 methods that we use. We based only on similarity, for example, producing a larger pool, and then from this larger pool, try to extrapolate the image that is more similar to the prior images. But we can also apply crossover, and there is more direct, let's say, influence. And as you can see, the image that is produced by crossovering these 2 images before, it resembles more the prior image than what was before. And again, we do repeat that for a number of generations, and then eventually we replace in the population. We have tried different technique for replacing. We replace a random is the easiest one. So we move random images in the population just not to have a population that increase extremely. So this is the result we did. If we compare the cultural selection and the bias transformation in the 2O, we also have included the random selection, actually not transforming the images, you're just mutating randomly. You can see the bias transformation is the only one that is able from initial population of random images, like the one in the bottom left, to start producing shapes. So you start, one may resemble a fish, other resemble a face or something like that. So there is some indication that the bias transformation can enhance actually and random images to something that is more interesting. What is missing in this work is a proper evaluation of these things. Here we just, me and a couple of my colleagues try to select some of the images. But if you want to expand a bit on this work, we'll be needed to build a more structured evaluation. So in these plots, they're also interesting because here I'm trying to plot over the generation what is the similarity between this specific experiment. I use 5 priors, the 5 prior images here. And in the plot is the average similarity that there is actually the average distance in this case, or the opposite of similarity of 50 images towards each. What is interesting is the different shape of these plots that came out, and this was a repeated things we found. So while cultural selection, it seems somehow to reach some sort of convergence at some point. Actually, he only mutate similarity in the first 10 generations or so, 50 generations in total we done. What's more interesting is happening with the biotransformation. You can see this fluctuation between similarity towards a certain prior, towards another prior. Have to remember that, remind that at each generation, these prior are selected, they alternate the selection of the prior. So what is producing a sort of tension, and it produces some more results that is a mixture between convergence toward a prior, but divergence, which fits really nicely with a concept like open-ended, important in creativity. Just to finish off, I got even try to transform in this these images at some point will get stuck, so you can produce more interesting images from the random one, but at some point the creativity seems to be exhausted. What it can be the next step is updating the prior. So it started with far the method was completely automated. We reached some results, we didn't reach rare things. But I say, what about if you start selecting new prior? So among these things that I selected some that I thought it was better, and then I restarted the process in 50 generation. By repeating this 1 or 2 times, start seeing even more, in my opinion, more interesting faces, more interesting images like that. And also importantly, I know and later, I have 15 seconds, the complexity of the CPPN behind by updating the power images is indeed able to increase as well. So also the complexity is evolving towards a more complex shape in terms of more connection, more layers, and more nuance. So for being a bit over, thank you for your.
Okay, we have time for a question or two right here.
Thank you for a super interesting talk, and it's so far outside my wheelhouse that this question may not make sense. But when I think of evolution, I think there should be some concept of fitness to determine which of your random generations make it into the next generation.
Okay, so
meanings of generation, yeah.
So yes, I should explain me better. So we don't have a fitness. So the idea is we want to generate creative images. So what is the fitness? Well, fitness is subjective. That's the first idea. So the one thing we thought is, okay, let's say we have 5 subjects. Everyone has got his own preferred image. That might be in terms of space. That is materialized by these priors. And these are the ones that are guiding. They are guiding the evolution of the images. In evolutionary network, as you say, in the fitness for each generation, it will be like the similarity to one of these selected images. So the idea is that instead of 5 images, you start having 50, hundreds, and thousands, that will create a much more variation. It's not, and the fitness at the specific generation will be towards one of these images, but then at the next generation, and that's, I think, is the interesting things, the fitness may be swapped to an image that is opposite. So you try to transform an image, my example that might resemble a car, because I'm the current fitness, my current motivation, my current taste is I like cars, and that instead at the next step, the leading fitness will be that for an animal. So what happens if you try to transform the shape of a car to an animal? So this is only partially successful, but it's also only a starting point of their work. So hopefully we'll be able to expand on that in the future.
Thanks for the talk. I might have missed this, or maybe it's in the paper, but you started talking about cultural evolution, and then we spent a long time biasing images. Is there a link back or a theory about cultural evolution that you're testing in this work?
Yeah, we tested these 2 different methods of the cultural selection. Cultural evolution about copying cultural models. You can do is the way of cultural selection. So I just try to imitate cultural models. I copy your model. I pick from the population the image that is more similar to what I like, and then I leave like the natural random mutation of this image. In theory of cultural evolution, at least in that one that we are following from Boyer Richardson, they said, okay, there is another important mechanism that is called guided variation. Here we're calling bias transformation. But the idea behind is that in this particular case, transformation and variation is not random, because culture is not mutated at random. Otherwise, it would have been as low as the biological evolution of Darwin. So the idea is that I take one image and I try to transform it according to my taste. If you want, if it was instead of images, if it was a tool or something practical, you can replace this guided variation with individual learning. So I got a knife and I try to get the knife more efficient. So in this case, the fitness is more direct. But if you think if many try to transform towards one direction, like having knives that are more efficient, so also the population becomes more biased and leaning towards that thing. So when the nature starts selecting a random model, you have more chances to select a random model that is already biased. So that's the links with cultural evolution. And again, this can be done more because there are also more complex theory of cultural evolution and so on and so forth.
Okay, thank you, Walter.
Thank you very much.
Okay, our next speaker is Daniel Lopez. He's going to talk to us about towards the automatic evaluation of visual balance for graphic design posters.
Yeah, it's fine. So, hello everyone. My name is Daniel Option. I'm presenting this paper named Towards the Automatic Evaluation of Visual Balance for Graphic Design Posters by me, João Correia, and Nosal Machado. So, one of the requirements for developing reliable and independent computational creativity systems is the ability to autonomously evaluate the aesthetics, at least for visuals. So, however, finding objective metrics to do it well, it's still an open problem. In graphic design, to properly evaluate artifacts, it is necessary to take into account a number of factors. For example, concept, legibility, innovation, and even whether the artifacts fit the personal taste of the target audience or public. And also visual balance is often a relevant feature to take into account. Building on top of existing work, in this paper, we have presented and tested a practical method for evaluating the page balance of graphic design posters. And to do that, a center of mass was calculated by taking into account the brightness and location of each pixel of a given graphic design poster. The closer this center of mass is to some predefined axis, vertical and or horizontal, the better. An overall evaluation value is by weighting and adding the obtained values for each axis. Different axes and combinations of axes were tested during the experiments. More specifically, we considered the vertical, horizontal center axis, the bottom margin axis, and considering the Western reading direction, we also tested the leftmost margin as an axis. And with these 4 axes, we tested a bunch of combinations, and some axes could have supposedly have a more visual weight than others. We also tested different weights for summing up the distances. To test the approach, we gathered a set of 120 graphic design posters created by different authors and gathered from various sources, such as posters designed by us, posters from the online archive, posters.colarts.edu, posters from well-known graphic design studios from their websites, and posters from this other online archive, typographicposters.com. And by means of a user survey, we asked graphic designers and CC practitioners to evaluate the posters. Each person evaluated 24 posters, 6 for each type. More specifically, they were asked from 0 to 10 how visually balanced they thought the posters were. Furthermore, studying the hypothesis of a correlation between page balance and visual pleasantness, the respondents were also asked from 0 to 10 how much they liked the respective posters. The results of the survey were then compared to the ones performed by the developed method. To or not our method could reasonably modulate human perception of page balance, at least according to the opinion of the respondents, and whether balance and pleasantness could be related to some extent. So to compare manual and automatic evaluation, we averaged the manual evaluation values and then calculated the average distance and also the cosine similarity between manual and automatic evaluation. The average distance was then inverted to become average similarity instead. So the closer the value is to 1, the better, as it happens with the cosine similarity. Average similarity indicates the present method match at around 80% the balance evaluation made manually, and the cosine similarity was a little bit more optimistic. Also, we can see the center axis often give better results. However, as the differences are very small, other combinations might be worth testing as fitness metrics to evolve layouts. By looking at these black shape posters we designed, sorted from worst to better evaluated, we can notice that most of the posters have their visual weight distributed on a single side or horizontal center axis, often on the corners. And most of the best posters have their visual weight centered or distributed on both sides of at least one center axis. This by looking at the best manually evaluated posters on the top, all the 120 posters, and on the bottom, excluding the posters we designed. The best posters have their weights centered or well distributed on both sides of the center axis, and the worst posters tend to have their weights distributed on one single horizontally, vertically, or both. Further by visualizing the differences between automatic and manual evaluation value posters. As we see here, the average difference was around 20%, again, indicating that automatic evaluation is on average around 80% aligned with the opinion of the respondents of this survey. Here on the top, we can see the posters the users and the system agreed the most, and on the bottom, the ones they disagreed the most. And looking at some of these, especially we can notice one shortcoming of our system, that is posters with dark background and lighter content should be inverted before being passed to the system as it is right now, since we consider darker zones heavier. So darker zones must be content, not space. So this is an issue. Apparent movement of the composition might be an important factor that is not being measured. In this poster, the composition looks falling forward if we read it from left to right. So people evaluated it badly. However, the inverse poster leaning back was well evaluated by people. So for experiments, in further experiments, we might also test diagonal axis. From the results, we can also conclude our method evaluates posters more optimistically than the average interviewees. For instance, only 14 were automatically under manual evaluation, and among these, only 2 referred to distances above average. So humans and the system disagreed here above average. Those posters are these in the image. So these posters were balanced, but the system considered their center mass was not fully centered. To explain it properly, a further user survey must be conducted. Nevertheless, looking at poster 2, we can deduce, for example, that page division might have an influence in the perception of visual balance. So in future research, we shall consider whether evident page divisions or other visual factors can have an influence in balance. Summing up, considering the present experiments, the proposed method demonstrated to match at around 80% the evaluation of visual balance made by the designers and CC practitioners that participated in this survey. Therefore, we believe the present method can already be worth testing to perform fitness assignment on automatic evolutionary computation systems. And also because assessing balance alone might not be, might be reductive to evaluate graphic design, we suggest complement with other metrics, such as for assessing legibility, innovation degree, the relation to a given concept. Moreover, the results suggested a possible correlation between page balance and visual pleasantness, at least for the current experimental setup. So judging from these results, visual balance might contribute to some extent, at least to the perception of visual pleasantness. However, there might be biases here, so further testing must be necessary to prove such an assumption. So next steps must focus on testing the present approach for fitness alignment in an evolutionary system, along with other complementary metrics, not just balance. And we must further study how different personal backgrounds or additional visual features such as apparent movement or hue and saturation may impact the calculation of visual balance. And thank you.
Questions?
Thanks for the talk. I was curious about the population of human evaluators, because center aligning everything is a very common thing for not but more expert ones tend to do sort of weirder things with balance.
I'm a graphic designer. I don't agree that center everything is the way to go. So we tested another other combinations of axes. For
Totally.
instance, I can show you if I can get there. Here.
Right.
Well,
But
from
who
my
are the
perspective,
human evaluators that are judging this? That's what I'm asking. I know you tested all.
sorry.
Who were the human
okay.
evaluators?
The human evaluators were graphic designers
Oh,
and
okay.
CC practitioners working on graphic design, because people like me and Cunha are engineers, not engineers, are working on CC. But we are designers, but there are people also like us, there are not designers and they do computational creativity. So those are also participated. But graphic designers mostly. So
Interesting.
but the thing is, I don't agree center everything is the way to go. So we have options here, using all the axes, like center, horizontal axis, or left center vertical axis, or leftmost axis, whatever is closer to the center of mass. So it's closer to the border, it's going to be the border, because the border, there's lots of posters which are greatly designed, which are not aligned. So I believe this is the way to go, but the results indicate the center axes are better, but the values are very close. So it's not, statistically representative. The other metrics must be okay also. In my system, I will use this all axes option.
Thanks for the talk. I'm curious about the correlation and the evaluation, and you about the disagreement between the human evaluator and the machine evaluation. I'm curious to know what was the visually pleasant rating for those two examples, because I saw these posters and I thought that was visually intriguing by, utilizing the negative spaces. So that's intentionally imbalanced in a graphic wise. And I wonder if what was a visually pleasant rating by the human.
So you mean how visually pleasant are these two posters according to the users? I don't have the values here, but I have the graphic with all the posters, which is this one. So typically it's very close, but this can be biased because people are evaluating, 24 posters, and they might be just, okay, this is 4, this is 4, this is 6, oh, this is 6 again. Balance and pleasantness also are very sometimes difficult to separate. And there might be a bias, like they might just be tired and just click similar values or something. So we need further research on this. I hope I answer your question.
Okay, let's thank Daniel again. little confusion for a second. We are not going to, we're going to hear now from Marinus Vandenover, who's going to talk to us about co-creativity between music producers and smart versus naive generative systems in a melody composition task.
Welcome everyone. My name is Farid van Oever. I'm a media technology graduate from Leiden University. In music production, digital audio workstations are the main tools for producers for making music. These tools primarily transcribe the transcribing of existing ideas and not necessarily getting inspiration. It's good. The integration of AI technology into DAWs could potentially solve this problem, but these are yet unavailable. With the recent developments in music AI, we wondered whether these systems impact the creative process and in which ways. Current evaluation methods do not go into this, as AI researchers tend to focus on the technical complexity of models. And when there are user studies, it's mostly about usability and user experience. And in these user studies, there are rarely comparator or controlled conditions. So a randomized crossover study was performed in which 30 music producers were assigned to 2 consecutive sessions in double-blinded random order, co-creating with a smart system and co-creating with a naive system. The smart system incorporates the user input when generating its expansion, and the naive system does not. Both systems look identical and have identical file sizes to avoid unblinding the researcher and the participants to the condition. And the participants were unaware of the differences between 2 systems. So 2 sessions, and in each session, the participant was creating 2 melodies in 40 minutes while actively collaborating with the assigned system. And at the end, participants completed a questionnaire in which they rated the novelty, value, and surprise of the outputs of the system and rated general applicability criteria. And these ratings were subsequently evaluated in a semi-structured interview. In the end, participants submitted the MIDI files they created and the ones created by the generators. The output from each system and the producer's intermediate melodies were compared for the changes in compositions, the dissimilarity, meaning the new AI generated elements, and the adoption of these elements into their intermediate compositions. The output from the naive system differed more from the input than for the input than for the smart system. Although the dissimilarity was higher for the naive system, producers adopted a significantly higher amount of smart suggestions into their intermediate compositions. Despite these differences, the changes that producers incorporated were similar for both conditions. The questionnaires and interviews reveal that participants considered the smart system that incorporates user input, they value that higher. But occasionally also the naive system was valuable. They also considered the smart system to be more novel, even though the outputs are more similar to their inputs. To conclude, the smart system was seen as more valuable and novel, and the participants' preference for the system was evident in a higher adoption rate. Despite these differences, the incorporated changes were similar for both conditions. We see that 2 operationally identical systems have both valuable but distinct differences. Participants particularly liked the smart system expansions related to their own melodies, but also they liked the unexpected suggestions from the naive system. What was also interesting is that these systems were passive, so producers had to actively request for melodies. They were seen as collaborators, approaching similar effects to working with other musicians in a studio. These findings highlight the importance of studying the creative process when we are developing systems for co-creativity, as evaluating those outputs against static metrics of quality is insufficient to understand its place inside collaboration. We must therefore be sensitive to the creative process. We also recommend that future studies draw inspiration from our approach by combining the quantitative and qualitative metrics and the controlled blind evaluation to accelerate research in evaluating co-creative systems. Thank you.
Yeah, awesome. I wanted to know, if you go back, I looked at the screenshots of like your tool. It looked like a phone screenshot. Was this a program they had on their computers or on their phone? And how did they get the files onto their DAW and stuff like that?
Yeah, so they were standalone applications. So producers exported their melodies from the digital audio workstation, and then they could upload it into this standalone application on their computer. And then subsequently just insert that back into the DAW.
Yeah, thank you so much for the talk. Very inspiring. So one thing I'm wondering is, when you're talking about smart versus naive systems, and you're talking about you basically not disclosing this information and the existence of the other system to that participant, I'm wondering, do people using the smart system recognize that something is happening that behind the scene that is changing? And from a designer's perspective, do you think it's a good idea to let them know that something is changing behind the scenes, that the AI is trying to adapt to them, both performance-wise and ethical-wise?
Yeah, what I was trying to figure out with the naive system was to see whether providing a suggestion, regardless of the context, is provoking in a way and interesting. And what was the case also, that producers tended to look for patterns in the naive outputs, even though they were not there. But yeah, no, I think your point is valid with a future study, of course, but it was not the intent here to communicate this, what was exactly happening. We just wanted also to have to test this assumption that any suggestion is useful.
Thank you. One more time for Marinas. I was so excited to have our next speaker that I got ahead of myself, but we're now gonna hear from Anahita Dusti, who will talk to us about transfer learning for underrepresented music generation.
Hello, everyone. Hello, everyone. My name is Anahita Dusti, and today I'm talking about our research on transfer learning for underrepresented music generation. Music generation in an ML context is using models trained on music data to generate novel music. There are many models available currently using different deep learning architectures, but in this work, we are using Music VAE as the basis for this research. Music VAE is a VAE variation autoencoder-based model, which is trained on melodies extracted from 1.5 million MIDI files. So the problem that arises with this model and others like it is data imbalance. These models generate music that is very similar to the composition of their data set. And different genres of music are not represented equally in this data set, either because they're very unique or specific, or they are new genres being created. We are interested, and our hypothesis was that these models, specifically Music VAE, will perform poorly for out-of-distribution genres. So we tried to identify an OD genre for Music VAE, and then gathered a data set of 100 songs and used different approaches, transfer learning approaches, to try to adapt this model to our new OOD data set and analyze the results. So for genre analysis, we had 4 data sets of 10 songs each. And what we observed after evaluating them on based on reconstruction accuracy was that we saw a considerable drop in accuracy for the genres that we considered or we suspected would be OOD. Especially for Iranian folk music, we saw a major difference at 43%, as opposed to 95% for synth pop music, which is a genre that is very represented in the training data set. So we moved forward with our research questions with Iranian folk music. Then of all the methods that we tried for adapting our model, conceptual expansion Monte Carlo tree search, which is a computational creativity-based approach, was the most successful. This is a method that is based on conceptual expansion. CE in this work is the method that we use to represent our search data, our search space, excuse me. This is predicated on the fact that we can create new knowledge by combining existing knowledge. And in this context, we can start from a an already trained model that we have, and by combining its weights in a particular manner, we can create a new model close to it, but different, that might contain new information and new feature extractors, for example. And then a Monte Carlo tree search is used to search that space. So in this problem, the root of this tree search is the music VAE itself. Music VAE itself, and then for each branching node, we use CE to expand upon that. And at the end, we use the most accurate models to evaluate. For our results, we observed that CEMCTS performed much better, especially on fold 4. We can see that it is recognizably outperforming conventional methods such as fine tuning. And fold 4 contains a lot of outlier data in terms of node density. Before I conclude, what we've come to is that a non-conventional method of transfer learning based on computational creativity may be helpful in adapting such models to new and more diverse music, and it has the potential that in the future be used to generate more novel and diverse types of music using the large generation models that we have. Thank you very much.
Thank you so much for the talk. I think my question is, I think you mentioned this maybe briefly in the beginning, but I know you use a data set with the equal number of songs per genre. I'm curious to know whether you think considering the variance in each genre should reflect the proportion of that genre in the data set. So for example, I would assume maybe a Bach chorale, like a set of Bach chorales has less variance than a set of jazz improvisation chorales. And should that mean that there should be more jazz in the data set than Bach, so the model could maybe learn more patterns in the jazz and the Bach? That makes sense.
Yeah, that's actually an interesting question. We haven't worked on the composition of data sets. And for the original music VAE data set, we don't have access to what it contains, only the pre-trained weights. And actually, I would like to talk more about that. It's something that we haven't done.
Lots of questions. This is the last one though, because we're And it's okay, you can get her at the coffee break.
I hope it's a good one then. I have a question also about the training data sets. So it is sort of an issue, I think, in music information retrieval that a lot of the training sets are genres that are quite regular and easier to train. I think this is going to this question about Bach chorale. So I'm just wondering, did you try any other, are there any training sets that were folk music based or more traditional music based? Because this is all sort of more electronic, and it would be interesting to sort of see if that was possible.
So other than the Iranian folk music, we haven't tested it with other folk music, but this one was particularly of interest because this is a very fundamentally different genre from Western music. It has different roots. It's not based on Western music theory. It would be interesting to test it on different genres, but for the evaluation part, we would need some sort of human subject study to be able to make assertions. I'm not sure if I answered your question.
Okay, thank you, Anahita. Okay, another lightning talk by Brian Wilson, exploring psychoacoustic representations for machine learning music generation.
Good. All right, good morning. My name is Brian Wilson. I'm currently a student at NC State University. I'm accompanied here by James Skripchuk, my fellow co-author and researcher, and unfortunately John Botcher, who's also one of the researchers on this paper. He wasn't able to be here, but he helped me out with this project. And so the title of this is Exploring Psychoacoustic Representations for Machine Learning Music Generation. So there's been a lot of talk recently about large machine learning models, LLMs, even yesterday. And even so if we look at this from a macroscopic view, right? Large machine learning models are just generally able to process very large data sets with a high dimensionality and a high number of features, a lot easier than smaller models. And because of this, they may yield better accuracy and a lower loss compared to smaller models. But this comes at a cost. So training these large machine learning models, that can be very financially expensive. They can consume a lot of power, and they can leave a very large carbon footprint. And so in our study, we looked specifically at machine learning for the purpose of music generation. So even with these models that are very large, they still suffer the same problems. And so we asked ourselves, is there a way we can inform the model through a new representation of the data that it may be able to mitigate some of these problems for large machine learning music generation training? And so we look at tension curves through a psychoacoustic lens. So essentially a tension curve is a graph that models the harmonic tension and resolution over a piece of music. And so you'll see on the slide in the top left corner, this is a tension curve for two pure tones. So essentially, if you have two pure tones lined up and you take one pure tone and you increase the frequency away from it, from the other one, what does the tension curve look like? So if you move right on the slide, this is a tension curve, same tension curve, but the two pure tones are now complex tones. So they now have overtones or harmonics. And so one of the main contributions of this paper is I essentially took that graph, that function, and I expanded it to include any arbitrary number of notes as well as some contextual information. So the research questions that we looked to explore in our paper was one, what is the impact of tension curves on model training time and performance compared to a symbolic representation? So that would be the precedence. And then in addition, we also wanted to explore if our new representation could offer any controllability of expressiveness on the output. And so we used some computational music metrics such as chord histogram entropy to kind of measure this. So this is the procedural pipeline. This is just for the tension curve representation. The control group, which is the symbolic representation, would be essentially just to take the Bach chorales and put it in the music transformer. One important thing of note is that we did train an embedding layer because the music transformer requires a tokenized data set to be passed through. And we were worried that this would kind of dilute the meaning of the tension curve representation being passed through the model. I can talk a little bit about that a little bit later if we have some time. So the results are pretty promising. For the model performance, not only did The accuracy and the loss converged quicker, about 30% quicker, but it did converge to a better value for both the loss and the accuracy, as seen with the tension curves on the slide. And then the model output suggests that some contextual information may yield some controllability of the chord variance of the output. And I could talk a little bit about that methodology if there's time at the end for that. So a brief recap of the contributions. We expanded the dissonance function, as mentioned on a couple slides before, to consider any number of notes and some contextual information to be able to make it applicable to all music. And then we proposed a potentially promising method to increase the model performance and controllability of the output through some human crafted features. And so some future directions that we thought would be interesting to explore. One, are what other representations of music other than tension may yield better training performance? And then two, what ways can we utilize some geometric transformations of the tension curves to yield some interesting outputs and potentially better model performance? So thank you so much.
Time for a couple questions. Oh, sorry.
So in this paper, you seem to have more or less mapped constant dissonance to tension. But there's, as you know, there's a bunch of other things that are also considered part of tension mechanisms, such as volume differences, right? And differences in embouchure and other kinds of things. Volume is the easiest one probably to pull out to extract from music. Are you specifically interested in dissonance and consonance measures, or where are you more interested in different kinds of tension throughout the musical performance? And if so, where are you going to be going with this?
Yeah, so that's a very good question. And I think that kind of maps to the one of the future questions we mentioned. So we looked specifically at a corpus of sheet music. And so you mentioned volume being specific one. I would even argue rhythm is another way you can kind of look at tension and resolution. That's kind of hard to kind of deduce and extract from just the sheet music. It'd probably be better to look at some live performances or some audio, but that would definitely be interesting to look in the future. I completely agree.
Okay, let's thank Brian again. We have two more talks and they are both remote. The first one is going to be a lightning talk by Jose Lopez. And after that, we have a full-length talk. Oh, they're both, are they? Okay, I lied, just kidding. They're both full-length.
Just a small disclaimer, this will be my student. And for those of you that were interested about emoji, we also go nuts about memes.
Yes, this is our second Inator talk of the day.
Hello, my name is Jose, and today I'm presenting Stonkinator, an automatic generator of mimetic images. Richard Dawkins coined the term meme as a transmission unit that holds an idea or behavior between human beings, crossing generational and cultural barriers. But nowadays, the term is associated with internet memes, that usually are images and videos from the internet containing humorous content. This type of communication has seen a rapid growth in digital communication due to the fast rate in creation and spread of these images. Other existing meme generators tools include ImageFlip's Meme Generator, a website offering a wide range of tools and personalization, ImageFlip's AI Memes, another website that produces captions for specific macro images, and AI Memes, a system that lets users choose from 10 images scrapped from the internet and generates 10 captions for that image. In terms of how memes are divided, there are different meme templates such as Matrix Morpheus. This is an image macro featuring a screen capture of a fictional character, Morpheus, with the captions typically following a two-line format, with the first line reading, "Where if I told you?", followed by some information that might be useful or not that useful. Another example is the "One Does Not Simply" template, which is another image macro showing the character Boromir from The Lord of the Rings, also typically following a two-line format with the first line reading, "One does not simply," followed by some kind of unwritten rule of life. These images can also be divided into different meme genres, which are used in different situations. One of these genres is called reaction shots, which are meant to portray a specific emotion in response to something that has been said. Existing meme generation systems usually allow the user to produce multiple types of output, making it difficult to determine the genre to which the meme belongs and understand how it should be used. In this paper, we focus on stonks memes, which are often used as reaction images and represent an excessive proud feeling over the completion of a simple task, as we can see in the examples. Our goal is to create a specific meme generator that can easily convey the user message by facilitating the creation of stonks memes to be used in social media and instant message conversations. As well as what happens with previous examples of memes, by analyzing these images, we can also observe a specific structure, which consists of a caption, a background, a person with a character's head, usually in a 3/4 perspective, which is called the meme man, and a related word with a typo. In these examples, the word stonks derives from stocks, and tech, chef, and health have their original wording more easily identified. We intend to create a system that receives only one textual input and could generate the final image automatically. Some of the advantages of having a system like this are its accessibility. The user doesn't need any design knowledge nor specific software to create these images. Efficiency. There's no need to manually analyze, select, and segment image elements. And diversity. By scrapping multiple images related to the input, the system is able to return different results each time it runs, whether it's a different retrieved word, background, or person in the output. The system is divided into 4 modules. Firstly, the system receives an input, which will be used as the caption of the image and sends it to the first module, the text handler. The first module analyzes the input sentence given by the user and extracts a theme or a subject, which is sent to the second module. The second module obtains a set of images related to the theme identified by the first module. The third module analyzes the images and selects one containing a person and another one to be used as background. It also resizes the images and creates a mask to be used in the blending process. Lastly, the fourth module receives the image containing the person, the background, and the mask, and performs the blending. It also writes the sentence used as input, the retrieved word related to the action, and places the meme man character's head in the place of the person's head. Going into more detail, the first module uses RakePython, a Python library to divide and rank the input into key expressions. Then it selects the highest ranked expression and using the library NLTK and the lexical database WordNet, tokenizes it, which is, in short, to transform the words into strings with a known meaning. Using these libraries, the system also finds hypernyms and synonyms and compares their meaning with the tokenized word. This process returns a list of words similar to the tokenized one, in order from the most to the least similar. The second module obtains images from Flickr, from the list of words retrieved from the module 1, and sends them to the next module. The third module, the image analyzer, searches for people in the images and divides them into background and person images. In case at the end of this process the system doesn't find any person or background images, the second module downloads more images until there's enough resources for the system to proceed. The third module uses the most libraries and models, including OpenCV, dlib's Hog Detector, ImageAI, and MediaPipe. These are used to filter the previous images, deleting the ones where human figures are too close or too far to the camera, and not in a 3/4 perspective. It also chooses the final images and creates a mask to be used in the blending process. The final module gets all the previous elements and uses them to create the final image, the system can perform 3 different types of blending. A simple pasting of the elements, the Laplacian blending between the background and the person, and the Poisson blending, also between the background and the person. For the purpose of testing, the Stonkinator was given a simple interface through a website using Flask for Python and hosted in a private machine. We intend on making the website available in the future. The testing was conducted during an early stage of the system and later improved using the feedback received. And the test tasks ask the participants to generate and evaluate the memes produced as well as to save them into the system. This is one of the outputs generated by the system during the testing. The results show that the outputs were unpredictable, and yet they convey the participants' message, which may indicate some degree of creativity. Participants also stated that they would use the produced memes in social media posts or during an informal test conversation. Some issues reported by users were mainly related to the size and font of the caption and written word, which made the meme hard to read. Besides that, this stage of the system also lacks the key element of the deliberate spelling mistake present in the examples shown before. Therefore, we developed an improved version. What we can see is the output of the current version of the system, in which we focus on fixing the issues previously mentioned. In terms of typography, we changed the use font with the intent of creating more recognizable memes. We used the impact font for the caption, which is widely used in these types of images, and to make them easier to read, we gave them variable sizes. We also introduced the spelling mistake, using the libraries Finsil and PronouncingPy to divide the words into syllabes and switch one of them with the corresponding phoneme. This allowed us to incorporate the typo mistake while letting the user know what would be the original and correct word. Although this version of the system hasn't been tested yet, these were some of the results produced by our system. Thank you.
I hope so.
Okay, so maybe we can have questions. Let's see.
There.
Hi. Oh, we do have Jose. Anybody have a question for Jose?
Hello, thank you so much. So I really enjoyed the meeting. Hi. And so it comes to show that certain memes are universally understood, but some memes are more contextual. How do you or would you account for that in terms of incorporating context within the memes that you generate?
Okay, so the idea for this generator was so people could share their experiences and I don't know, whatever they wanted to share. So that's the input for the caption, and that usually gives the context to the person about the image below. Our idea with the Stonkinator was to make a more restricted output, so they are all in the same format of memes, so people could more easily create and understand what the meme was. I hope I have answered your question.
Any other questions? Okay, let's thank Jose again. Thank you, Jose. We wish you were here. Okay, we have one more talk now. We're actually just a slight bit ahead of time now, so hopefully this talk is ready. Is this live or a recording? Do we know? It's a recording. Oh, it's ready then. Sweet. Yes, let's go ahead. This is a talk by Simon Colton about neurosymbolic generation of music with talking points.
Hello there, I'm Simon Colton, and this is joint work with Burka Benar and Sarah Cardinali at Queen Mary University of London. I'm talking today about neurosymbolic composition of music with talking points. So this is a systems description, and the system is called Parley. And I'll start with a couple of disclaimers. We're not really that interested in the quality of the music produced by the system. And we really don't want to create music that sounds like someone else made it. So we don't really fit into the current dominant narrative from generative deep learning. The real aim of the project is to automatically add to musical culture, and we have an Ivo Muzart paper about that. If you think about it, generating music has many applications, only one of which is to have more music. So I've been influenced by the work of David Bruce, who's a fairly well-known British composer. He also has a YouTube on which he undertakes composition tasks, but he does so for education and entertainment. So he's adding to musical culture there, not just through the music that he produces, but through education and entertainment. So if you think about how an unimportant theorem in mathematics can actually be proved with a powerful new technique, then the theorem's not important, but the technique is, and that can get added to the mathematical culture and be a big part of the toolbox for mathematicians. That's what we're trying to do with music with this project overall. A secondary aim is to provide an open source platform for experimenting with neurosymbolic generative approaches, where we mix deep learning with more traditional AI approaches. And I'm personally interested in generating both audio and score representations of the music. I think that pieces of sheet music can be beautiful artworks in their own right. So the kind of written note is very important to me. Here is a paper from Ivo Muzart if you want to know what we mean by adding to artistic cultures. We're not talking about that a great deal today. We are going to be discussing talking points, which is similar to that. I wanted to show you the state of the system by giving you an example output from it as a video. Please listen to this music and watch it scroll by. Have a look at the notes in the margin, because they're the kind of talking points that we are discussing, and see whether you can, see what you think about this music. Okay, so I have to stop the music there, but hopefully you could see the margin notes going by with some talking points. You could possibly hear the crescendo from the start episode to the next one, the accelerando, and hopefully you can agree that it's fairly acceptable, fairly interesting music, but nothing special, and certainly some rough edges still there. To get to this stage, I've implemented the fundamental processes required for generating bars of music. So structured generation for episodic music with quite precise timings. You can have precise timings on the volume from bar to bar, episode to episode, and tempo, the speed. And there are elements of expressive performance, like the sustain pedal being used for the second episode. Hopefully you could hear that. It's a neurosymbolic approach, which I'm describing in this talk, where modules design, generate, edit, analyze, and frame the output. And I've got it so that it export to various representations. It produces like 25 files for each piece. MIDI, music XML, PDF for the score, audio files like WAV and MP3, and MP4 videos like you just saw. This is all generated directly from pressing go on the system. There's no third-party apps used to generate this. Of course, I do use software like MuseScore to generate the score, and they're all credited in the paper. Importantly, it can frame the music with talking points about it. It's an open source development in Python, which is horrible, but hey, the benefit of that is I can regularly port this to Colab notebooks so that everyone can run this, including the GPU elements which are required. In total, we want Parley to produce proper sheet music with expressive performances. We're not interested in music as an exercise for machine learning, where it's all about producing MIDI files which fit the representation, or note sequences, that kind of thing. We want to celebrate music and innovate with it using this approach. Now, I've mentioned it's a neurosymbolic approach, so there are various modules which are rule-based symbolic modules, like the dinosaur approach, and there's others involving pre-trained neural models, just like the cool kids are using these days. Now, the benefit of that is that some things can be dealt with by symbolic means, rather than relying on prediction from a model. So in particular, it turns out that if you can handle discordancy, so there's not a massive clashing discordance going on, not crazy repetition or weird intervals or odd rhythms, then you're halfway on the road to producing an acceptable sounding music. If you think about all the music talks you've been to where the music has been really difficult to listen to, it's usually discordancy, repetition, crazy intervals or weird rhythms that are causing the issues. And you can handle those with a symbolic approach. However, on the other hand, the pre-trained neural models, they're trained on human music. So in a loose sense, they have a trained ear and they're not dependent entirely on rules. So that means they will probably introduce novelty and surprise if and done in the correct way, that could produce really interesting music. Most importantly, the neurosymbolic approach has much more texture to the generative process. So there's more opportunities for explanation, education and entertainment, and cultural additions hopefully later on down the line. And again, see the Evo Musart paper if you're interested in our argument about why neurosymbolic approaches are good. In the paper, this is an excerpt, I point out that if you read a book on musical composition or watch some YouTube videos about it, you'll get three types of advice in general. The first type of advice will be to follow rules and heuristics of music theory and practice. So here's a way of generating some sequences. Here's how to do modulations, that kind of thing. Voice leading melodies, that kind of thing. And that will get you off the ground with producing some music. However, you're also told to constantly make choices based on listening to the emerging composition. They'll say, here's some advice, listen to the music. Does it sound right? Does it sound right within the genre? Does it sound right for this particular piece? Does it sound right for your style? So you can make some edits based on just what it listens to without necessarily following the rules. And then finally, you'll be told, make sure your music isn't super repetitive. Make sure it's got some innovation and novelty in there. Or if it's crazy, make sure it's a bit more coherent. Add some things in which flow from episode to episode. And I think that these three bits of advice can be achieved by symbolic AI, rule-based modules for the first following rules approach. I think we can use pre-trained neural models which can listen to the music and make suggestions to make it sound better according to what better means. For the second, making choices based on listening. And for the third, I think we can use old AI techniques like constraint solving and planning to achieve consistency, coherence and novelty across the music. And in Pali, there are cycles of design, generate, edit, analyze, frame, and export, not necessarily in that order, and they produce music with talking points. Now, what do I mean by talking points? Well, I named the system Pali because I thought the word Pali was ancient pirate lore for having a meeting where you sit down and chat. And there's a picture there from Pirates of the Caribbean where they are having a parley. Turns out that that word was basically invented for the film Pirates of the Caribbean, and no one even knows how to spell it. But the point is that I want to produce things we can talk about, not just a piece of music which sounds good, but things on top of it which can actively encourage to talk about that music. So we're not very concrete about what we mean by a talking point at the moment, and this is a criticism of the paper, which is fair enough, but we want to get feedback from the community first. Obviously, this fits within the explainable computational creativity notion of framing, which myself and others have looked at over the years. At the moment, it includes points of interest. The talking points include points of interest and points of potential concern, which might want to be re-edited, and general information to help understand the processes. Currently in the system there are talking points through the color coding of note types in the scores. You saw that in the video to start with. Some bars are highlighted as being most improved in terms of the pitch class listening model. So it takes a bar, changes the notes in it, and one bar will be more improved according to that listening model than another in terms of the likelihood of the classes of pitch in there. The other talking points include warnings about discordancy, overly discordant pieces, and repetitions of chords in a sequence. They also include interesting artifacts. We saw one of them in the video at the start, which was introducing a sextuplet rhythm. That's quite a talking point for a piece of music. And finally, there are comments on the aural nature of the music via mood tags. So Pali can say that this bar or this piece episode is relaxing or deep or calm, that kind of thing. I haven't got time, unfortunately, to go into details about the current set of modules that I've implemented. Please do see the paper for details about that. So there's designers, generators, editors, and analyzers for doing form, chord sequence design, generating voice leading melodies, passing note generation, that kind of thing. There are editors which take an existing piece of music and improve upon it. Like with discordance, getting rid of some discordancy, finding and editing awkward rhythms, getting rid of overly repetitive areas, and adding in things like taking two quavers and a crotchet and turning it into a tuple, a triplet. And finally, there's analyzers which can tell you about the mood, or the pitch class analyzer where the best bar has come. And there's also areas of rhythmic analysis there. So please do see the paper for detail of that. The 4 in red there all involve neural models, which are the listening models that we've implemented in TensorFlow, the ones in red there. And the first set of listening models we have are LSTMs trained to predict the pitch class of a note given a seed sequence leading up to it. So these were trained by Bernard originally to find interesting outliers in human composed music. He has one for the 18th century music corpus and one for 20th century music. And I repurposed the first one of these for what I think is a novel way of generating music using LSTMs. Basically, you produce a acceptable piece of music, albeit a bit boring, using a rule-based approach, and then you go through it and you edit each note, you edit the pitch class to try and improve it as per the listening model, because the notes leading up to that note plus all of the history encoded into the model will tell you which pitch class is most likely given that lead into it. You have to wrap the melody around to get notes leading into the start of the piece and the episode, but still it works quite well. And I found that works really well, in fact, in terms of adding novelty to the music. It's very difficult it's too easy to predict before this, and afterwards it's really quite novel and less obvious to predict, and with the right constraints it doesn't make too many errors, so it doesn't introduce clanging, howling notes very often, which was surprising. The second set of listening models we have are from the Gemendo mood theme tagging model from the amazing Essentia package that the Music Technology Group at Universitat Pompeu Fabra have produced. So what happens here is that it produces activations for 50 tags, word tags, including emotions like dark, genres like ballad, settings like in space, and use cases like a movie trailer. And it works on the audio in a 2-stage process, raw audio. It first compresses the audio to a latent space, and then it takes a latent vector for a piece of audio to make predictions to get the activations for those 50 tags. So what we do with Parley is we generate a MIDI file. We then use the MIDI file to produce a WAV file. Then we compress that WAV file to an MP3 file. We pass that MP3 file through the first of these neural models to get a latent vector, a latent representation of it. And then we use that latent vector to get the 50 activations, and we use that information in the composition process. In the paper, you'll see that I've exported this to a Colab notebook. And that has 6 cells. Please see the paper for more details. The first cell tells you what the lead sheet is, what the chord sequence is in the piece. This is for the flaneur pieces. And it also highlights as a talking point there the fact that you've got 6 or 7 E minors in a row, which is probably too many for that piece of music to not sound repetitive. So it outputs the score as well as an audio file which you can play with the play button there. In cell 2, it adds in accompaniment in the left hand and a melody in the right hand, and it tells you that the green notes are the chord tones, which we call the backbone notes, and the orange notes are the passing notes that's added in. So each of these cells has multiple modules running in it to generate the next draft of the music. And it tells you to look at bars 16 and 18 as talking points because they don't have any passing notes in them. They're only backbone notes. Cell 3 is the first time the listening model is used, and in this case it tags the episodes as being melancholic, dramatic and sad respectively as talking points, and it highlights some bars where it's particularly melancholic. In cell 4, it does the editing of the notes in order to improve the pitch classes according to the listening model. And it highlights there that bar 19 is the most improved. The blue notes haven't changed, they've not been edited. The green notes have been edited to be improvements, and the purple bar is where the most improvement has happened. Cell 5 adds a harmony to the right hand and also does a discordance analysis and tells you about the discordances. So the red notes there in the second bar are an F and an E, which are clashing because they're only one semitone apart, as is the other one at the end of that segment. So it warns you about those discordant notes, but it doesn't fix them. In the final cell, it does some orchestration. So there's lots of experimentation I did offline to get it into a position where it can choose the instruments to use in order to achieve a particular mood. The user chose the word deep here, and the software chose guitar and synth for the two different parts to this piece. And it produced an exceptionally relaxing, a quite calm, and an exceptionally deep piece as a result, according to the listening model. Okay, I'm having to rush, I'm afraid. I can't talk about the experiments, but we did a load of experiments in order to find out about this neural editing process. How does it work with different setups, and what are the musical qualities of the music produced? Hundreds and hundreds and hundreds of pieces produced. Please see the paper for an analysis of this. Berker and I found this very, very interesting, but I do realize that it was just a wall of numbers in the paper. So do contact us if you're interested in that. Okay. For future work, and we want to further explore the listening model approach to automatically generate symbolic music in this neurosymbolic way, because we think this is a new approach which is a fair contribution. It's time to hand over creative responsibilities in version 2. So Parley is more like a composition tool at the moment. The user provides the largest specification file of about 300 lines of Python, and then it generates the music, and that is highly customizable. And soon, Parley will generate its own specification files. That will be done over the summer. It's all set up to do that. The first study will be the production of a set of piano etudes, like Chopin and Heller, but definitely not imitating their style. And we'll have to look really hard about the notion of patterns in music in order to achieve that. Okay, I'm a little over, sorry about that. Thanks for listening, have a great conference, and I think there's time now for a few questions, or you can ask me on Twitter, there's my handle. Thanks for listening.
Do we have Simon here for questions?
I think so. Simon, hi.
Okay. Hello, Simon. Who has questions?
Hi.
Oh, yes. We have a couple. Just let me get it over here.
Thank you for a very interesting talk. And
Thank you.
I have one question that comes to my mind is, can you elaborate how you handle repetition? As you said in the presentation, a piece must have some repetition in order to have a coherence, but not too much. So do you have a module or something like that that handles the repetition so that it has a correct amount of repetition?
Yeah, sure. I mean, I have this kind of allergy to lots of generative music. And one of the things which is difficult for me is repetition of the same note or the same short passage over and over again, notwithstanding the great music by people like Philip Glass. And so, yeah, it's actually both. So a number of the modules have repetition checking in them or constraints in them. So when you do the neural editing, the changing of the pitch class, it may well be that it's changed that class to be the same note. It's changed a note to have the same pitch as the one previous to it. And that can be constrained out. So you've got a number of options for the change. You just make sure you don't change that, that note to be the same as the one previous to it. And that will minimize the repetitions that you get. Similarly, when you're doing passing note additions, you can be at the end of bars, you have to be clear how to do the handling of repetitions there. And there's actually a whole module which can go through a piece which hasn't had this done to it and edit the repetitions. And there's 3 or 4 different ways you can edit them. One, you can tie the notes, so you get one long note, so it's not a repeated note. Others, you can just put a rest in for the second note. The third way is to make one of the notes staccato, so you get a bit more of a rhythm in there. And these can all be chosen randomly if you want those to happen. There's probability in there so that sometimes the repetition is left in, sometimes it's not. And the user can highly customize that handling of repetition. So it means that I get pieces now which don't jar because of endless repetition. And that when you're doing the neural editing, you often do get a lot of repetition because it's choosing one note based on the previous 50 notes. And that doesn't change very much from window to window to window. So often you get repetition, and that's why the symbolic approach enables me to get rid of that. I hope that answers the question.
Great talk. I wanted to ask about talking points. I like the concept. I was wondering if they seem very sort of declarative. I was wondering if you considered discussion questions possibly, because like if I'm in a class, like you saw something where it's like the sextuplets, and I think it said like grindy or something like that on the sheet
Yes,
music.
clang
So
and grind.
yeah, so I was wondering like possibly discussion questions like, do you think this works in this context, or would you use this on one of your pieces? Have you considered any of that for like a more classroom or even music appreciation type approach?
Yeah, absolutely. In fact, in the paper, the first discussion point is a question. Are 7 E minor chords in a row too many? So it's left there, and you can choose to regenerate, or you could edit it directly, but it's put there as a discussion question. So yeah, absolutely, I think that's a really good idea to mix it up, enable people to take ownership of this music. The whole point of the discussion points is to increase engagement. And when Burke and I have been looking at this music, we have actually been chatting over the music itself, not just the process and all the AI going into it. And so we were quite pleased at one stage that we were actually using these talking points to start discussions about the music itself. And yeah, absolutely, a classroom environment would be great for this. Actually, I'd like to try that out.
Hey Simon, great talk. It's a shame you're not here to continue the conversation.
I have massive fear of missing out, FOMO. I'm really sad not to be there. Sorry about that.
Anyway, so I got two quick questions, or the first one is rather quick, I think. So you said you were looking at both audio and like symbolic generation, like the MIDI, but the audio you mostly like just synthesize from the MIDI, right?
Yes, the generative side is for sure.
Okay.
At the moment.
Just wanted to confirm that. And
Okay.
so for now you only looked at piano pieces, is that right too?
No, no. For the demo, for the video, yes, I've been looking at piano pieces. Largely because I've not really got great sound fonts, and I do have a great sound font with decent piano in it, and I don't wince at the quality of the music. But in the Colab notebook and in the paper, I've done some experiments offline with instrumentation combinations. So combinations of pairs of different instruments from about 120 from a sound font, including all the brass, the woodwind, the string instruments, percussion, and so forth. Actually, not percussion, because you don't get pitch with that. And so there is a module in there which can take one of the 50 tags from the mood theme model and choose between a list of really good options for instrumentation for that music. So that it achieves, or at least according to the listening model, it achieves the mood that you're looking for. And I'm beginning to trust those listening models. I've been trusting in vision models for quite a while now, but I'm now beginning to trust more the listening models than my own ear. But no, it can work with 120 instruments from a sound font at the moment.
Hi, Simon. This is a really interesting method of combining different rule-based and AI systems. Well, but it seems like one of your goals is trying to avoid imitating the style or of certain types of music. But there's obviously some rules and methods that likely have some connection to some biases or real rules that are from some kind of style. I guess my question is, so how are you actually trying to avoid replicating the style? Is it just because you're combining all these models just to push each other in different ways?
Yeah, I'm not actively avoiding it, but I'm not actively attempting to do it. So we don't start with a corpus of Chopin pieces and attempt to learn the style or the patterns from those. But I'm not sure it's going to be easy to achieve proactively finding these new styles. But I mean, we can look at creative adversarial networks, which is relatively old work now, not of mine, where they try and generate pieces which are not easily classified into classes visual art in that case. And I think an approach like that might work. There's loads of listening models now which will choose the genre of your music, and it's very good at telling whether something is jazz or pop music or classical. And I think we can probably hack those to tell you when a piece of music is not quite fitting into any genre. And that will be very similar to the creative adversarial networks approach. That might be a way of being more proactive about it. But at the moment, I'm just concentrating on getting enough rules in there. I didn't mention it in the talk, but in the final slide, I have this tokamak particle accelerator. And I want the generative process to go crazy, just be absolutely full of energy. But I want the listening models to be the magnets around the tokamak, keeping everything in place. So I'm hoping that when I let it loose and I hand over the creative responsibility of choosing all of the parameters for the specification file, that it will invent forms of music which at least are novel to me, but they sound okay because they're kept in check by the listening models. And that will be a good start. It will be like P-creative. It'll at least be creative to me, and hopefully maybe fairly interesting to the musical community.
Okay, great. I think it's a good place to wrap up for the coffee break.
Thanks a lot.
Thank you, Simon. Let's clap for Simon. Hopefully you can hear.
No, but I can imagine. Thank you.
All right, thank you. See ya. Okay,
Bye-bye.
everybody, thanks for a good session. Let's go to coffee break. I think that's time, right?